Hi everyone and welcome to this tutorial on meta learning using one-shot learning, MAML and Meta-SGD algorithm. So let's get started with the outline of this tutorial. First, we will begin with the simple introduction to meta learning types and categories. In section 2, we will talk about one-shot learning techniques and algorithm. In section 3, we will discuss the model agnostic meta-learning denoted by MEML. In the next section, we will talk about MetaSGD, stochastic gradient descent, as an efficient algorithm of meta-learning. Of course, finally, the conclusion. Deep learning has progressed rapidly in recent years with great algorithms such as generative adversarial networks denoted by GAN. But the problem with deep neural network is that we need to have a large training set to train our model, and it will fail probably when we have very few data points. Which brings us back to a main question. Is deep learning really the true AI? Well, it is not. So let's see, how do humans learn? We generalize our learning to multiple concepts and learn from them. But current learning algorithms master only one task. Here is meta-learning comes in. We train our meta-learning model on various related tasks with a few data points. So let's see now the types of meta-learning. Of course, we can categorize meta-learning in different ways, but the main types are learning the metric space. Also, we can learning the initialization, and of course we can learning the optimizer. In the next section we will discuss these categories with some examples. So let's get started with learning the metric space, one-shot learning as an example. So learning from fewer data points is called few-shot learning or K-shot learning, where K denotes the number of data points in each of the classes in the dataset. If, for example, we have exactly one dog and one cat image, then it is called one-shot learning. That is, we are learning from just one data points per class. In the metric-based meta-learning setting, we will learn the appropriate metric space. Let's say, for example, we want to learn the similarity between two images. In the metric-based setting, we use a simple neural network that extracts the features from two images and finds the similarity by computing the distance between features of these two images. This approach is widely used in a few-shot learning where we don't have many data points. As an example of metric-based learning algorithm, we can say that Siamese network is one of the simplest and most used on one-shot learning algorithm. Also, there are relation networks in one-shot learning. It consists of two important functions: the embedding function denoted by f and the relation function denoted by g. The embedding function is used for extracting the features from the input, and we pass these combined features vectors to the relation function g, which will generate the relation score ranging from 0 to 1. representing the similarity between symbols in the superset and symbols in the query set. The overall representation of relation network in one-shot learning setting is shown in the presented diagram. Matching networks are yet another simple and efficient one-shot learning algorithm. Published by Google DeepMind team, it can even produce labels for the unobserved class in the dataset. Look at the following diagrams in the picture. As you can see, we have three classes in our superset: lion, elephant, and dog. And we have a new query image. First, we feed the superset to embedding function G and the query image to embedding function F, and learn their embedding and calculate the cosine distance between them. Then we apply a softmax attention over this cosine distance. Then we multiply our attention matrix with one hot embedding superset labels and get the probabilities. And then we select y height as the one that has the highest probability. Now let's talk about learning the initialization and MAML as an example. Model agnostic metalearning is one of the most popular used metalearning algorithms. The basic idea of MAML is to find a better initial parameter so that with good initial parameters, the model can learn quickly on new tasks with fewer gradient steps. In MAML, we try to find these optimal weights by learning from the distribution of similar tasks. So for new tasks, we don't have to start with randomly initialized weights. Instead, we can start with optimal parameter. The overall algorithm of MAML is shown in the following diagram. The algorithm consists of two loops: an inner loop to find the optimal parameters theta for each of the tasks, and an outer loop where we update the randomly initialized model parameter by calculating gradient with respect to the optimal parameters in a new set of tasks. Now let's talk about learning the optimizer metastochastic gradient descent as an example. Unlike MAML, MetaSGD will not just find the optimal parameter. It will also find the optimal learning rate and an update direction. So in MetaSGD, we don't initialize a learning rate with some small scale value. Instead, we initialize the learning rate with random values with same shape as theta and learn them along. So we sample some batches of tasks, and for each task we sample some key data points and minimize the loss using gradient descents. So as you can see, MetaSGD is just a small tweak over MAML. In MetaSGD, we're not just learning the model parameter theta, but we also learning the learning rate and update direction. Finally, the conclusion. In this presentation, we try to answer three main questions. What is meta-learning? What are the benefits of metalearning, and we can say that flexibility and potential for fast adaptation from little data, and what are current meta-learning approaches. And we discover that there are three main current data point approaches: metric-based meta-learning, model-based meta-learning, and optimization-based meta-learning. Finally, meta-learning challenges. Of course, there are many challenges faced to meta-learning techniques, and we can say that the main challenges are meta-overfitting when task variability in the training data is too low. Also, there are meta-underfitting when task variability is too high. Of course, the computational cost during the meta-learning pre-training phase. We finish our tutorial with frequently asked questions. Question 1: how is transfer learning related to meta-learning? Question 2: how is multitask learning related to meta-learning? And question 3: how fine-tuning allows for effective meta-learning? We will try to answer this question in the next tutorial. Thank you for watching us, and see you in the next video.